We can start now as many of you have checked in. So once again, hello everyone. Welcome to our webinar on TinyML and Firmware Demystified, powering AI on minimal hardware. My name is Vandana Dharmarajaram, Senior Firmware Engineer at Decos, and I'm delightful to have you all here. Thank you for taking the time to join us. So without further ado, let's dive into this critical topic. So, before moving further, let me quickly walk you through our agenda for this session. We will start by understanding what TinyML is and why it's important. Next, we will explore the TinyML workflow and the key technologies that make it possible. After that, we will take a closer look at some of the most widely used TinyML frameworks. Once we understand the fundamentals, we will move on to real-world applications of TinyML across industries. To make things even more exciting, we will have a demo where you will see a TinyML model in action on a microcontroller, showcasing how AI can run on ultra-low power devices. Finally, we will wrap up by discussing the future of TinyML, the latest industry trends, and the opportunities this technology brings for businesses and developers. So let's start by understanding what TinyML actually is. TinyML or tiny machine learning refers to the process of running machine learning models on small, low power devices like microcontrollers and embedded systems. These devices typically have limited processing powers, memory, and energy consumption, yet with TinyML, they can perform AI powered tasks right at the edge without relying on cloud computing. To put it simply, TinyML allows us to bring AI to the smallest of devices, enabling real-time decision making while consuming minimal power. This is a game changer for applications like smart wearables, industrial automation, healthcare monitoring, and even environmental sensing. Unlike traditional machine learning, which requires powerful cloud servers or GPUs, TinyML enables models to run directly on microcontrollers that often operate on just milliwatts of power. This makes it incredibly efficient for battery powered devices and IoT applications. Here are some differences between TinyML and traditional AI/ML model. So the first difference is hardware and computational resource. TinyML runs on low-power microcontrollers, for example, ARM Cortex-M, ESP32, with limited memory, typically less than 1 MB RAM, and processing power, while the traditional AI/ML model runs on high-performance GPUs, TPUs, or cloud-based servers with large memory and high computational capacity. Next difference is in power consumption. TinyML is optimized for ultra-low power consumption, typically milliwatt to microwatt range, enabling battery-powered, always-on application. While the traditional AI/ML model requires significant power, typically watts to kilowatts, making it unsuitable for battery-operated edge devices. Next difference is in latency and real-time processing. TinyML performs inference locally on the device, leading to low latency, real-time decision making without relying on cloud connectivity. While the traditional AI/ML model often requires data to be sent to cloud or edge servers, introducing latency due to network communication. Next difference is in model size and optimization. TinyML uses compact models with techniques like quantization, pruning, and knowledge distillation to fit within microcontrollers' constraint, while the traditional AI/ML model can use large deep learning models, for example, GPT, ResNet, BERT, without size limitations. Next difference is in connectivity and data privacy. TinyML processes data locally on the edge device, enhancing privacy and reducing reliance on the internet, while the traditional AI/ML model requires cloud or server-based processing, which may raise privacy concern and increase data transmission cost. Next difference is in application. TinyMLs are used in IoT, wearables, environmental monitoring, smart home devices, and predictive maintenance, where power efficiency is critical. While the traditional AI models are used in big data analytics, autonomous vehicle, NLP, for example, ChatGPT, cloud-based computer vision, and large-scale business applications that demand high computational resources. And the last difference is development complexity and deployment. TinyML requires expertise in embedded systems, model compression, and hardware-specific optimizations, while the traditional AI/ML model primarily focus on data science, deep learning model training, and large-scale deployments in cloud and or enterprise environments. Before moving further, I have a poll question for you. You will get 30 seconds to answer this. The question should be displayed on your screen now. So the question is, what makes TinyML ideal for edge devices? As you can see, many of you have answered the question. So option A and B both are incorrect because TinyML is designed for low power devices and it runs locally on edge devices. Option D is also incorrect because TinyML model perform on-device inference. So the correct answer is option C, that is low power and memory usage. Reason, because TinyML is specifically designed to run on resource-constrained edge devices such as microcontrollers and low-power processors. These devices have limited memory and computational power but can still perform AI inference efficiently. Now I will walk you through the TinyML workflow, explaining how machine learning models are designed, optimized, and deployed on tiny, low-power devices. The TinyML workflow consists of 5 key stages: data collection, model training, model optimization and deployment, on-device inference, and continuous learning. TinyML model follows a structured process to ensure that AI model can run on resource-constrained hardware with minimal power consumption. Let's start with the first step in TinyML workflow, that is data collection and pre-processing. This step is crucial because, as the saying goes, garbage in, garbage out. If our data set is not clean, accurate, and well prepared, our TinyML model won't perform well. So let's break it down. TinyML model rely on data collected from various embedded sensors. This sensor capture real-world information and convert it into digital signals that our model can process. For motion detection, we use accelerometer or gyroscope. For sound-based AI, we capture data from microphones. For image-based classification, we use low-power cameras. For environmental monitoring, sensors like temperature, humidity, and air quality sensor collects reading. Once we collect the data, it needs to be clean and prepared before training our model. This ensures that the model learns meaningful pattern instead of noise. So the first step in pre-processing is noise reduction. Raw sensor data is often noisy due to background interference. We apply techniques like smoothing filters to remove unwanted fluctuations. Second step is feature extraction. Instead of feeding raw data to the model, we extract useful features. Third step is data augmentation. To make our model more robust, we artificially increase the size of our data set. In image-based TinyML model, we can flip images, adjust brightness, or crop the image to create variations. For time series data like accelerometer reading, we shift or scale the signal to simulate different user movement. And the last step in data collection and pre-processing is data labeling. Supervised learning requires labeled data. If we want to train a keyword spotting model, we need labeled audio samples of different words. For a motion classification system, we label accelerometer data with tags like walking, jumping, or running. Now that we have collected and pre-processed our data, the next step in the TinyML workflow is model training and optimization. This is where we teach our model how to recognize patterns and make intelligent predictions. Let's break it down step by step. We choose a machine learning algorithm such as neural networks, decision trees, or support vector machines. The model is fed with input data and the correct output so it can learn relationship between them. The training process involves forward propagation, where data passes through the network, and backward propagation, where the model adjusts itself by minimizing error. Now, what happens during training? The model continuously adjusts its parameter to reduce the error. The performance is evaluated using accuracy and loss metrics on training and validation dataset. The training process stops when the model reaches an optimal performance level. Now, next is the optimization techniques. Traditional AI models are large and require powerful hardware. But in TinyML, we need to make them small, fast, and efficient to run on microcontrollers. That's where model optimization comes in. Now we'll see the key optimization techniques. So the first technique is quantization, which is basically shrinking the model. By default, model uses 32-bit floating point number, which require a lot of memory. Quantization reduces this to 8-bit integer, making the model smaller and faster without losing much accuracy. This reduces RAM, flash storage, and computational requirement. Next step is pruning, which is basically removing the unnecessary weight. Many deep learning models have unnecessary connections that don't contribute much to accuracy. Pruning removes less important weights, reducing model size while maintaining performance. And the last technique is knowledge distillation, which is basically training a smaller model using a larger one. A large complex model is trained first. A simpler, smaller model is then trained to mimic its behavior. This allows us to retain high accuracy with much smaller model. Before we can run our model on a microcontroller or an edge device, we need to go through the crucial step of model conversion and deployment. Most machine learning models are trained on high performance computer, but edge devices like microcontrollers have very limited memory and processing power. That's why we need to convert our model into a lightweight format. Now the question is how to do this. If we train our model using TensorFlow, it would be in a format that is too large and complex for an embedded system. To make it suitable for edge deployment, we use TensorFlow Lite, that is TF Lite, which convert it into much smaller, optimized format. But even TF Lite is too heavy for microcontrollers. That's where TensorFlow Lite for microcontroller, that is TFLM, comes in. This further optimizes the model to run on tiny, resource-constrained devices. Next is deploying the model to an embedded device. Once we have the optimized model, we need to load it onto our target hardware so it can start making predictions in real time. There are some steps to deploy a TinyML model. So the first step is to transfer the model to the device. The converted model file, for example, .tflite, is uploaded to a microcontroller like ESP32, STM32, or Arduino. This is done using programming tools like Arduino IDE, Edge Impulse, or TensorFlow Lite micro APIs. Second step is to integrate the model with firmware. The ML model is embedded in the device firmware. It connects with sensor to receive real-world input and make inferences. And the third step is to optimize for real-time performance. Ensure the device runs efficiently without crashing or slowing down. Use hardware accelerators like Google Coral Edge TPU or NVIDIA Jetson Nano for more intensive tasks. Now, after training, optimizing, and deploying our TinyML model onto an edge device, it's time for most exciting part, running the model in real time. This process is called on-device inference. Inference is the process where a trained machine learning model takes in new data and makes prediction. In TinyML, this happens directly on the device instead of a cloud server. Now, how does on-device inference work? So first step, the edge device collects sensor data. The microcontroller receives input from sensors like microphones, accelerometers, or cameras. This raw data is then pre-processed, for example, filtering noise, normalizing values. Step 2, the model makes prediction. The processed data is fed into a deployed TinyML model. The model analyzes the input and predicts the most likely outcome based on its training. Step 3, the device takes action. Based on model's prediction, the microcontroller executes a predefined action. Action could include turning on an LED, triggering a sound, sending a notification, or activating a motor. To maintain accuracy, the model needs updates and refinement. Some devices support incremental learning for continuous improvement, while some periodically collect new data to refine the model, and some updates model remotely with OTA updates when needed. Before moving further, I have another poll question for you. Again, you have 30 seconds to answer this. The poll question should be displayed on your screen now. The question is, how do you optimize TinyML models for minimal hardware? Okay, so option A is incorrect because more training data improves model accuracy but does not directly optimize it for minimal hardware. Option C is also incorrect. More layer increases model complexity, making it harder to run on resource constrained devices. Option D is also incorrect because high resolution input demand more memory and processing power, which is unsuitable for TinyML application. Yes, so the correct answer is option B, that is quantize and prune model. Reason, quantization reduces model size by lowering precision, making it efficient for low power hardware. Pruning removes unnecessary weight and neurons, reducing computation and memory usage without significantly affecting the accuracy. Now, TinyML frameworks provide tools and library that allow us to train, convert, and run machine learning model on ultra low power microcontrollers and edge devices. Let's explore the top TinyML framework in detail. So the first framework is TensorFlow Lite for microcontrollers. TFLM is a lightweight version of TensorFlow designed specifically for running machine learning models on microcontrollers. It supports low power devices with only kilobytes of RAM and provide efficient inference capabilities. Now, why use TFLM? Because it supports quantization, making models smaller and faster. It works on microcontroller like STM32, ESP32, Arduino Nano 33 BLE Sense. It is optimized for ARM Cortex-M CPUs, RISC-V, and DSPs. Next framework is EdgeImpulse. EdgeImpulse is a TinyML development platform that simplifies data collection, model training, and deployment on edge devices. It provides a no-code, low-code interface for beginners while allowing advanced customizations for experts. Now, why use EdgeImpulse? Because it has cloud-based training with drag and drop interface. It supports real-time data collection from sensor. It deploy model to MCUs, DSPs, and accelerators easily. It support AutoML for TinyML. Next framework is PyTorch Mobile and MLKit. PyTorch Mobile allow you to run deep learning model on mobile and embedded devices. While it is not directly optimized for microcontrollers, model trained in PyTorch can be converted for TinyML deployment. Key features are good. It is good for rapid prototyping of AI model. It supports quantization aware training to optimize for low power devices. It requires conversion to work with TinyML microcontrollers. Now, what is MLKit? MLKit is a set of pre-trained AI models from Google designed for mobile and embedded application. It allows on-device inference without requiring cloud access. Some of the key features are it requires no training, that is, it is ready to use model. It works offline on mobile and embedded devices. It supports text recognition, object detection, and face detection. Here are some of the applications of TinyML. The first application which we will discuss is healthcare monitoring. Wearable devices equipped with TinyML model can analyze heart rate, temperature, and movement patterns at the edge. In healthcare, reducing latency in detecting abnormal patterns could lead to life-saving interventions. These devices also offer privacy since sensitive health data is processed locally rather than in the cloud. Next application is industrial automation. In manufacturing, real-time monitoring of machinery is critical to avoid downtime. TinyML enables predictive maintenance on edge devices by analyzing vibration, temperature, or other sensor data, detecting potential failures before they occur. Next application is in smart agriculture. TinyML on edge devices can help monitor soil moisture, temperature, and other environmental factors to optimize irrigation and fertilization processes. These solutions can operate in remote areas with limited or no internet connectivity, making farming more efficient and sustainable. Next application is consumer electronics. In smart homes, sensors and cameras can use TinyML to detect patterns such as movement or voice command without sending data to the cloud. This allows faster, real-time response in applications like smart lighting, thermostat, and security system. Next is our demo, which is motion recognition based on edge impulse. Here are the software setup which we require for the demo. That is, we have to install Arduino IDE latest version. Next, we have to install Node.js version 12 or higher, create an edge impulse account, and we also need a data forwarder. This is the hardware setup. We are using Seed Studio board with Nordic NRF 52840 ARM Cortex M4 processor running on 64 MHz frequency. It has 256 KB RAM, 2 MB onboard flash memory. It has onboard 6-axis accelerometer PDM microphone. It also has Bluetooth 5.0. We also need a USB Type-C cable to connect the board with the PC. So due to time constraint, I have made a video of the demo. First, we must launch the raw accelerometer data code in Arduino. So this is our code. Then we have to navigate to File, then Preferences, and fill the additional board manager URL with our board package, and click OK. Now navigate to Tool, Board Manager, type the keyword seed nrf2 and install the appropriate board packages. Now choose the correct board and then compile and run. So this is the raw accelerometer data. Now we have to send this raw data to Edge Impulse. For that, we will open command prompt and run the Edge Impulse data forwarder command. Here we have to type the username which we have used in Edge Impulse. Next, type the password. Choose the appropriate COM port. Select the project name. Now name all the 3 axes. We are naming it as AX, AY, AZ. Now if the connection is successful, our Edge Impulse will look like this. Select the sensor with three axes, label up and down, sample length to 20 milliseconds, frequency 50 Hertz, and click on start sampling. During this time, we have to swing our board in up-down motion for 20 seconds. You can find the acquisition is shown up like this. Now we have to split the sample. For that, click on the three dots, click split sample, click on add segment, and then click on the graph. We have to do this for more than 20 times to add segment. Then click on split. Now you will see the sample data each for 1 second. We must repeat this step for other motions as well. Now click on dashboard, drop down page to find perform train test split. Click on that, choose yes, and confirm it. Click OK. Again OK. Now we have to create impulse. Click on create impulse. Add a processing block, choose spectral analysis, and for the learning block, choose classification and click on save impulse. Now click on spectral features, drop down page, click save parameters. Click on generate features. At the bottom, you can see the feature generation output. Now click on classifier, keep the settings by default, and click on save and train. You can see the training output at the right hand side. Okay, so the precision of the training model is very important. If your output training results are as low as less than 65%, it is highly recommended to train for more times. Here you can see the cluster of different motions. Now click on model testing and click classify all. At the right, you can see the model testing output. So our accuracy is more than 90%, which is good. Now click on deployment. Click Arduino library. And for the compiler, select Eon compiler. And click build. A .zip file will get downloaded. Now we have to add that zip file in the Arduino libraries. For that, click on include libraries and add .zip library. Here you have to include the downloaded zip file as I have already added, so I will cancel. Then You have to change the name of the header file as the name of your own, and you have to compile and run. So this is the final output. As I'm moving my board in up down motion, you can see the green LED glows both on the hardware and the GUI as well. Now I'm moving in left right direction, so the red LED glows. Now I'm moving in circular motion, so now the blue LED glows. So this was our demo. As we have explored the fundamental of TinyML, including workflow, optimization techniques, and framework, let's now take a look at what the future holds. TinyML is rapidly evolving and several trends are shaping its future, from improved hardware to new AI models optimized for ultra-low power devices. The development of ultra-lightweight ML models like TinyBird, MobileNet, and SqueezeNet is accelerating. These models are specifically designed to run on low-power microcontrollers while maintaining high accuracy. There are advances in MCUs with built-in AI accelerators. Traditional MCUs are evolving with built-in AI accelerations for faster TinyML inference. Companies like ARM, ST microcontrollers, and Qualcomm are producing MCUs optimized for AI. Now there are key development in AI hardware. ARM Cortex M55 and Ethos U55. These are first microcontroller class core designed for AI acceleration. RISC-V-based AI chips, these are open source hardware architecture enabling custom TinyML chips. Google Coral, HTPU, and NVIDIA Jetson Nano, these are AI accelerators bringing edge computing to embedded system. Next is AutoML for TinyML. Now what is AutoML? Automated machine learning, that is AutoML, helps in model selection, training, and optimization without manual interventions. Tools like Google's AutoML Edge, Edge Impulse AutoML, and OctoML allow developers to optimize model for embedded systems without needing deep ML expertise. Next is TinyML plus 5G. 5G brings ultra low latency and high speed connectivity, allowing TinyML devices to communicate with cloud only when necessary. TinyML devices can process data locally, reducing network congestion and cloud dependency. Next is Edge AI plus TinyML, the future of smart devices. Edge AI is pushing TinyML to the next level by enabling real-time AI-driven decision at the device level. Next is business opportunities and industry adoption. Industries like healthcare are adopting TinyML for wearable health monitor, easy early disease detection, while manufacturers are adopting for their predictive maintenance, smart homes and cities for their AI-driven home automation and security systems. Now, why companies are investing in TinyML? Because it reduces cloud computing costs, that is, the AI inference happens on the device itself. It enables real-time decision making, that is, there is no dependency on cloud latency. It enhances privacy and security, that is, the data stays on the device, which reduces the risk. As more as more industry adopt TinyML, we will see a surge in AI-powered devices, making smart technology more efficient and accessible. At Decos, we specialize in integrating software into embedded systems, ensuring real-time responsiveness, reliability, and security. Our expertise encompasses firmware development using C, C++, Linux, RTOS, and peripheral device drivers. We adhere to industry standards such as ISO, EMI, EMC, IEC, and ANSI, ensuring that our firmware solutions meet regulatory requirements and quality benchmarks. We assist in preparing the necessary documentation to demonstrate compliance, helping you navigate regulatory audits smoothly. Our team is available to provide ongoing support and guidance, keeping you updated on the latest firmware trends and threat intelligence. By combining our expertise in hardware and software, Decos delivers innovative and reliable firmware solution that empowers organizations to achieve their technological and business objectives. So that is all for today. I hope you liked the content delivered today and I was able to give you a brief insight on TinyML and firmware. For any questions, you can contact us. The contact details are on the screen. Please note a recorded version of this webinar will be available on our website within a week. We will also send you an email with the link on your registered email ID to access this webinar. Thank you for your time. Have a great day. Bye.